Okay, we're going to go use table A6.1, and we're going to find the standard reduction potentials that will help us calculate the value of K at 25 degrees Celsius for the following. Well, that's quite a mess now, isn't it? Let's look at this. Here's iron on this side and iron on that side. You know what? That is not in the order where it would be reduced, right? Because the number went up from +2 to +3. So when I go look in the table, I should be looking for iron 3+ becoming iron 2+. So when I get to the table and I do look that one up, the 3+ with an electron as a reduction potential becoming iron as a 2+, I will look up a number that says 0.770 volts. Okay, wonderful. That means the other one I shouldn't have to turn around because it's always one that's reduced and one that's oxidized. So when I look up the other one, which is already in the correct order, what I find is it's a little more complicated than what I would like to see because, okay, well, it just is. It says there's 5 electrons involved, and at first that kind of worries me because I didn't have 5 electrons in the last one. But I go and I look this up and I find that it is listed as being 1.507 volts. And like I said, the 5 kind of worries me for a minute. Then I go back and I look at the equation and I realize there's the 5 right there. It was that this equation had to be multiplied by 5. And remember, that does not mean this gets multiplied by 5. It is still the way it is. This is about the quantity, and this is about how far it falls as far as its energy. All right, wonderful. I think I've convinced myself then that N is going to be equal to 5. Now, what is the value for the cell? Well, I always take the one that's more positive. That would be the 1.507. And then I subtract the value that I found for the other one because it was a reduction, but it has to be listed as an oxidation. That's why we have the minus. So we subtract this. And when we do that, we're going to find that we have 0.737 volts. Excellent. Now, we had said something about what the log base 10 of K was for an equation. We said that we were going to use N, and then we were going to use E. And on the bottom then I had, well, oh yes, they say this is at 25 degrees Celsius. So okay, I can go ahead and just use the 0.0592 and that'll be fine. So when I do that, I get a number. I wanted the value of K. This is the logarithm of K. A logarithm is an exponent. And in this case, it is an exponent of the number 10 because we said this was a log base 10. So 10 to the 62.247. When I run my calculator on that, I get an absolutely massive number for K. This favors the product so much that we used to just say runs to completion, which makes sense. We want our batteries to run to completion. We don't want them stopping early. It was the more we can have them run, the better. Now, what you might have noticed from this is that K, E cell, and delta G cell are all related. We have 3 formulas. We had one from an earlier chapter. So that one was that K was related to delta G in this way. And that was an earlier chapter. When we had that delta G was minus N, and here's Faraday's constant, and the voltage on the cell. And now we have this one, that log of K is equal to N, and the cell voltage over 0.0592, and that's assuming that your temperature is 298 Kelvin. But we have these 3, they're all related, and so we can use the potential, E, in order to tell us what the equilibrium constant is. And that's what we just did. It allows us to calculate values of K that are incredibly large or incredibly small. Otherwise, we would have a very difficult time measuring molarities and so on to do that. But if we can set it up in this way, we can measure them when they're very, very large or very small. And we have a little table here that sort of summarizes things. I'm going to start at the bottom. If K is 1, things are in equilibrium. They favor neither the products nor the reactants. The energy of the cell ends up then being 0 because the logarithm of 1, you know, okay, we get a 0 here. That also means we get a 0 for delta G because it's not going either direction. It's just sitting there. We have the difference between delta G and E. It has a minus sign. So whenever we see a positive value for E cell, we're going to see a negative value for delta G. If we are generating a voltage, it's because there's a Gibbs free energy that's favoring it. And why is that happening? Because K is larger than 1 and it's saying, let's move on. Let's get on to those products. If we have a K that's less than 1, it's like, nope. We just as soon stay at reactants, and then the E of the cell is negative, or I've hooked it up in the wrong order, right? And the delta G of the cell is like, no, I'm not favoring this. We're not moving forward. We'd rather be back at our reactants.